This is HRW98P042. The worker pushes a block along a level floor at a constant speed with a force directed 34 degrees below the horizontal. I've gone ahead and made a free body diagram of this. So here's the force of the worker, normal force, which I forgot to label, sorry, gravity, and of course friction. Notice it said constant speed. That means that the acceleration, hello, wake up. The acceleration has to be 0, which means the net force is 0. Just keep that in mind. Okie dokie. Well, heck, if the net force is 0, that means that in the x direction, these two things are going to have to cancel out. The net force in the x direction, is 0. Then I need this and this to cancel out. So that means that the portion of the force in the x direction, the worker pushing, is going to have to, so minus friction is going to have to equal 0. So they should be the same magnitude. Okay, so that's F cosine theta is going to have to equal the frictional force, which is mu times the normal force. Well, the normal force is going to be, I'm going to get that from the net force in the y direction. That also has to be 0. So I've got normal force up minus gravity down minus the portion of force that's in the y direction. Okay, that's all got to equal 0. So the normal force is going to end up equaling mg plus f sine theta. Okie dokie. Alrighty. If I put n in over here, right over here, then, oh, I forgot the friction over here. Oh, no, I didn't. No, I didn't. I'm good. Okay. If I put this in over here, I get that new color, because this is getting put in right there. I get the force times the cosine of theta equals mu times mg plus f sine theta. Okie dokie. I want to solve for f so I can get it, and then I'll be able to work backwards and figure out some stuff. So let's see, solving for f, I need to distribute mu, and then I need to move this over here. Wow, that's becoming a subscript for some reason. No, it's not supposed to be a subscript. There we go. Okay, distribute mu. I don't think this green is showing up very well. Combine like terms. Okie dokie. So I'm going to have on this side, I've got f cosine theta minus mu f sine theta equals mu mg. I need more room. Boom. Okay. Pull the f out. F equal, or, pull the f out. Okay, and divide by all this nastiness. Go on. And I know all these numbers, so we just plug them in, and I get, oh, I didn't write it down what mu was, though. Mu is 0.2. So let's just write that down here. Go on. Alrighty. Now I've got it. Alright, so I get 0.2 times 27 times 9.8 meters per second squared over the cosine of 34 minus 0.2 times the sine of 34. Lovely, lovely. Calculator time. I get 73.79 newtons. Go on. Which, if you remember, way from the beginning we said the f cosine theta would equal the friction. So the friction, let's go back to this. the friction was equal to the x component of that. So that's going to be F cosine of 34. I'm going to take this. I haven't cleared it off my calculator yet. I'm just going to use it from my calculator right in there. And what I get is that the frictional force is 61.17 newtons. Now, I did a little bit more work than I really needed to. For instance, I really only need to solve for this, so I probably could have made this a little simpler somewhere, but I like to know what the force is just because I like to label my free body diagram in the end. Oops, because I'm a wacko. I like to label things. Yeah. There, now it's labeled. I feel better. All right. Well, if this was the force of friction, if I want to know how much work was done by the worker's force, well, the work done by the worker's force is the portion of his force that was in the same direction as the way the box was moving times the distance it went. So it was moving. Go on, turn the page. There you go. It was moving horizontally. So I need the x component of F. Again, I only needed the x component. The x component of F times the distance it went. It went 10.4 meters. Okay. So, by the way, those are the same thing. So I need to do, the work is the force in the x direction times the distance he went in the x direction. The force in the x direction is what I just found. The distance he went is 2.4. So I put that together and I get 636. 630, well, it rounds to 636 anyways, joules. Now, the increase in the thermal energy of the block floor system, when we talk about increase in thermal energy of anything, you're really talking about the work done by friction, because friction does negative work, taking the energy out. Well, where does the energy go? It becomes thermal energy. So basically, the work done by friction is the force of friction times the distance that we went. Well, the force of friction is the same as the x component of the worker's force, so I'm going to get the same number in the end. Okay. Another way to think about this is if the worker did this much work, another color, the worker did this much work, but none of the energy of the box didn't change. I mean, it didn't rise or fall, so the gravitational potential energy didn't change. It was at a constant speed, see? So the kinetic energy didn't change. So if the worker put this much energy into the box by doing work, but the box's energy didn't actually change, that 636 must have gone somewhere else. It must have become thermal energy. That's really the only default answer. If you have energy that seems to have been misplaced, or it seems like you need a place to misplace it, that place is thermal energy. Okay.